Okay, we'll continue. Okay. Well, yeah, thanks so much for the invitation and the nice introduction. Yeah, so I'll be talking about, as Miguel mentioned, about leading jets and energy loss, and all of that really just in the vacuum. But it can sort of be a baseline for basically then extending this to heavy ion collisions. At the end, I actually also have some data from the ALICE collaboration that's already in heavy ion collisions. So this work that I'll talk about is in collaboration with Daphne from Los Alamos and Nobuo Sato from Jefferson Lab. Okay, so let me start sort of with a big picture. Like eventually, what we would like to do ideally in heavy ion collisions, or if you're thinking more ahead in the future at the electron-ion collider, is basically this ideal scenario that you can see here on the left, where that's of course not something we can directly do in heavy ion collisions, but it's something we could do like in AMO physics and things like that, or condensed matter, where you basically use a laser beam that has sort of like 100% intensity at the beginning, then you like shine it at some probe, and some of it gets like scattered, absorbed, and so on. And then you can measure like how much of the beam is still basically gets through on the other side. So in this case, you say have like 40% left, and that means you have basically lost 60% of your energy. And then that 60% that you lose is something you can directly relate to the properties of the probe here in the middle. And that's sort of the ideal scenario that we would like to have. And that was sort of our motivation to think about leading jets and energy loss and try to see how we can get as close as possible to this, that we can really associate a number with the energy loss and say, you know, it's like 60% energy loss in, say, heavy ion collisions as well. And so energy loss, of course, is something that is people have been working on for a long time. Also, you know, of course, here in Santiago, people have done a lot of work in this direction. And this really goes way back to the 90s, where people basically thought about energy loss in sort of the soft and collinear limit. And so what that means, or the way I've been thinking about it in this context, is that you basically look at these kind of diagrams here, where you start with some initial, well, in this case, a quark that has a particular energy or transverse momentum Q, and then you emit a lot of soft gluons along the way, and at the end you measure basically the leading parton that is still left over afterwards, and you measure its energy, or the ratio relative to what was available at the beginning. And then the energy loss is basically all those soft gluons that you emitted here along the way. So the definition would be of energy loss then would be that you just sum over all those soft gluons, or that would be 1 minus the energy of the leading parton at the end. And that's something that one can do theoretically, both in the vacuum and in the medium, but it's basically tied to the soft limit. Only if you're really here in the soft limit, it's easy to do these calculations because it's very easy to define what is the lost energy. It's all the soft gluons, and the object that is still there at the end is basically the leading parton here, and it's the same as we had here at the beginning. So in this sense, we can directly say what energy loss is, sort of as a sort of theoretical concept. But of course, the problem is that if we measure anything really in heavy ion collisions, it's never going to be just QCD in the soft limit. And so the problem is that in that sense, it's basically not something that we can directly observe and really like quantify, similar to say AMO physics and say, you know, 60% or something. And that's of course something that has been known. And so what people do instead is of course to measure like jet quenching as an inclusive jet RAA. And that basically means that you take all the events, you count how many jets do you find in the entire event. So it's like an inclusive measurement over all the jets per event, and you put them in histograms. And then you look at basically the nuclear modification factors. So you compare PP and heavy ion collisions. And then you find, you know, overall there's like 50% less jets than you would observe in PP collisions. But there's basically no, it's of course like indirectly sensitive to energy loss, but we cannot really assign a number of like, you know, the 60% that I mentioned at the beginning. So that is sort of lost here. So it's of course a very useful measurement, and it's something that can be controlled theoretically very well. So it's great, but we cannot associate this number. And so we've basically been thinking about how we can associate a number of 60% energy loss, for example. And so in order to do that, so we went back to this picture, and we're not really actually changing anything about the definition. We'll keep the definition, we're not changing anything. It's just that we're basically trying to go beyond the soft approximation. And so that basically means we still start with an initial, say, quark, and then we measure the leading parton at the end. And so we still define energy loss in the same way. It's always 1 minus the leading jet momentum fraction. So anything that's not contained in the leading jet, that's what we would call energy loss. And so to do that, we have to go basically beyond the soft approximation. So we have to basically go to the full collinear dynamics. So we don't require anymore that these gluons are soft, and we of course also have to allow for flavor changing processes, and so basically look at the full evolution. As it turns out, that makes the calculation a lot more complicated. But the advantage of it is that we can actually write down a probability distribution. So if you were to basically deal with inclusive jets, I'll get back to that later, you always have to think about number densities. But if you think about leading jets, you can write down from first principles really a probability distribution to find a momentum fraction, say Z1 in your leading jet. And then from that probability distribution, we can here weight it by the momentum fraction Z1 integrated over the allowed range. And that really gives us then an average quantity for really the energy loss, or here the momentum fraction contained in the leading jet. And so that would really then be as close as possible. QCD allows us to go to really assign like a number and say, that's 60% energy loss of my initial quark or my initial gluon. So that's basically the main goal. We want to assign and measure such a number to really quantify at the cross-section level what we really mean by energy loss. So in this talk, I'll not, as I mentioned, not talk about any medium effects at all, but just first of all try to establish some cross-sections, how we can measure energy loss in the vacuum. And then from there on, of course, one can go ahead and change that also to heavy ion collisions. So when we thought about this, it seems, or we realized there's basically three requirements that need to be fulfilled to sort of make really a jet energy loss measurement at the cross-section level. The first one is, I already mentioned that, we need to basically look at the leading jet over here. And it's really important to look at the leading jet. Only in that case we can write down a probability distribution, or more generally, it basically has to be a fixed number of jets. Like we could also, for example, look at the first 2 leading jets and define as energy loss anything that's not contained in the first 2 leading jets. But what does not work, you cannot write down a probability distribution if you don't fix the number of jets. So if you look at an inclusive jet sample, you count all the jets, then we just cannot write down a probability distribution, and then we cannot do the measurement. So in this sense, we always need to have a well-defined single or object. So that's basically the simplest thing we can do to look at the leading jet only, and that basically is the object that has lost the energy. The second is, if you want to measure energy loss, of course, we need to have a reference scale. We need to know how much energy was initially available so that we can actually say how much was lost. And that, depending on basically your collision system, can be a little bit tricky to define, but we think we found at least some ways to do this. One way one could do it is basically to look at the photon here that recoils the leading jet. So you can measure that transverse momentum, and you can then look at the leading jet in the opposite hemisphere. That process has a little bit of problems, but I'll get back to that later. There's other ways, for example, using jet substructure, how one can also get at this quantity. And then lastly, we also require that at leading log, we can identify what we measure as jet energy loss at the observable level, that we can identify it with parton energy loss. And so the analogy here would be similar to the variable Bjorken X in deep inelastic scattering, where also there at leading log, you can basically identify Bjorken X with basically in the parton model with the momentum fraction of the struck quark inside your proton. And so what we would like to have is basically this analogy between the parton energy loss and jet energy loss that we actually measure. And it turns out that only for some cross-section, this is actually that it has the structure, and for some of those that wouldn't work. So if we basically if we can identify observables where all these 3 requirements are met, then we can basically call this energy loss. And if you then have sort of universality, then there should really be a sort of a universal quantity that we can measure an experiment. Just as an aside, let me just mention leading jets are also relevant, not just for energy loss measurements, but in many cases, you actually measure a jet substructure, not on an inclusive jet sample, but you measure it on, for example, the first leading and the second leading jet in these atlas measurements. Also in heavy ion collisions, there are measurements, for example, of the jet shape or the jet radial profile, where you now do measurements on the leading jet and the sub-leading jet. So if we're able to compute leading jet cross-sections and sub-leading jet cross-section, that of course is also relevant in other cases. It's also potentially relevant for quark-gluon tagging. If you think, for example, about leading subjets that can basically give you some ROC curves that do pretty well, and it's basically, it would be a discriminant that's relevant for or that you can control theoretically very well. So it can be relevant for that. There's also rather interesting connection to other fields where there's this whole literature basically on just breaking randomly breaking some objects. And then if you basically ask the question, what's the leading fragment, then that's very similar to basically asking what's the leading jet in QCD. And so it turns out that by basically changing or thinking about the fragmentation process, not in terms of inclusive jets anymore, but in terms of leading jets, since we're able to change to probability distributions instead of number densities, we actually find a lot of analogy of the QCD fragmentation process to like other fields. We found here, for example, one paper from the 80s, and that whatever they looked at there in like spin glass condensates actually looks pretty much like what we find for the leading log jet function. So it's kind of interesting. And of course, since we have probability distributions now, we can really connect it to a whole lot of like different statistical quantities that with number densities we couldn't access basically. Okay, so this is the outline for the rest of my talk. I'll talk about leading jet cross sections, how we can do the calculations, why it's more difficult than inclusive jets. And then I'll show numerical results about energy loss. And at the very end, I also have some recent results from Alice, where they basically did sort of the first measurements in this direction. Okay, so before going through basically how we can compute leading jet cross sections, let me say a few things about how we can do inclusive jet cross sections. There's different ways. Sorry, I'm trying to put the video somewhere else. Okay. So there's different ways, of course, to do inclusive jet cross sections. What I'll show here and what we use for the calculations is like a soft Coulomb effective theory framework, just because that's sort of easier for me to do. But in general, you can derive this without soft Coulomb effective theory, and probably doesn't even notice really that it's soft Coulomb effective theory sort of along the way. So the way I would compute inclusive jet cross sections basically by writing down a jet function and then putting that jet function into a factorization theorem. And so if we do the jet function calculation here at next to leading order, we basically just have two partons. They can be either clustered together into a single jet or into two separate jets. And then the jet function, similar to a fragmentation function, basically just measures the longitudinal momentum fraction that's contained in the jet relative to the initial parton here. And since this is an inclusive cross-section, we basically just have to sum over both possibilities, no matter what the value of z is. And then we can basically do a computation of this at next to leading order. And then so if you then basically look at the entire jet function distribution, say for a gluon with a given radius plotted as a function of this momentum fraction z, then you find this kind of distribution that has a peak at z values very close to 1. That basically just means if you have a jet, as opposed to say a fragmentation function, is very likely that you'll find a large fraction of the initially available energy in that jet. So that's why you basically get a peak here. And so we'll find something very similar for leading jets later on as well. And then it sort of goes down. It's quite likely you find some smaller fractions of that as well, because you're eventually reconstructing all the jets. So if we then change the radius, then we'll find something like this. So if we basically make the radius smaller, it's more likely that that initial jet will be basically split up into multiple jets. And so this peak slowly disappears, and you get basically an enhancement here in the small z region. And sort of this change from large jet radius to a smaller jet radius, that is basically then described by evolution equations. And as it turns out, the evolution equations for these inclusive jet functions are also just the regular QCD DGLAP evolution equations that you would normally find for fragmentation functions. And so that basically allows you to do both. Actually, you can even go pretty much all the way down to r equals 0. In that case, you just have a single hadron, and then you can basically get to fragmentation functions. So there's a complete analogy basically to that. So that's sort of at the jet function level, and then we still have to compute a cross section, so we need a factorization. And also here, the factorization for jets is really the exact same as you would get for collinear fragmentation functions or for hadron production. So if you want to know the cross section for inclusive jets, differential rapidity and transverse momentum, you basically have to take into account two PDFs, a hard scattering function, and then the jet function in the final state. And that then basically allows us to compute the inclusive cross-section. So there's basically these three steps: the NLO computation, QCD evolution, and factorization. And they're basically the same to all order. It's the same structure, and you just then have to basically compute higher order terms in this. Okay, so now how does it look like for leading jets? So the first thing is that the jet function basically at next leading order ends at z equals a half. And so the way to see this is that now basically we're only going to take, so this diagram is as before in next leading order, but here we're only going to take into account one of those diagrams depending on whether the quark or the gluon is more energetic, but not both. And so effectively what that means, if I want to write down the leading jet function that I always denote by this curly j, the other ones are the regular j. All I have to do really at next to leading order is still quite simple. I just really have to multiply this here with a theta function requiring that z1, the leading jet momentum fraction, is larger than a half. And so what that does basically is that if I just do a fixed order computation, it basically just cuts the spectrum here at a half. It's the same over here as inclusive jets. If I find a jet over there in that region, it's automatically the leading jets. I don't have to do anything, but the spectrum would basically be cut off here. And then if I basically go to higher and higher order, I basically slowly fill in like this region. It basically always goes to 1 over n plus 1 if I, when I compute higher and higher orders. Or what I can do is just do the resummation that will also effectively fill in that missing region to the left of a half, basically. So at NLO, it's still relatively simple to think about leading jets, and that's sort of where we started from. I then realized it's a lot more complicated if you want to think about the evolution and about the factorization. And so the first thing is that if we basically think about leading log or leading log prime, then it turns out that the evolution now becomes nonlinear. So it's still similar to a DGLAP evolution, but it's a nonlinear DGLAP type of evolution. So what it means, if I now want to know how the leading jet function changes with respect to mu, then I have to compute this expression here on the right. And basically what it is, it contains still the ultra-rayleigh parity splitting function, but then it contains two jet functions here on the right. So that means it's nonlinear. And to understand sort of where this nonlinearity is coming from, let me try to illustrate that here in this diagram here, where I just basically put some branching fractions that happen at each splitting according to the ultra-rayleigh parity splitting function. And then I basically look here at the end, which one is the leading jet. And so if I were to just do inclusive jets in this picture, I would just take all the 4 jets and I would put them in histograms, and that's it. But here now I of course need to compare. If I put a jet into a histogram for the leading jets, I need to know that it's actually with the leading jet and that was actually produced from this evolution. And so if I want to basically find the leading jet here that has momentum fraction, the largest momentum fraction, I need to find this green path. And that basically means in this particular example, I cannot at each branching just follow the more energetic one. I cannot go, to the 0.6 here, but actually I follow the sub-leading one, because eventually that will lead to the overall leading jet in the entire branching process. And that's basically what makes it nonlinear. So I need to know at each branching, if I want to find the green path, I need to know at each branching here the actual momentum, the branching fraction at that particular point. But I also need to know, if I follow this one, what's going to be the leading jet. And so that's basically why I have 2 jet functions here and then a splitting function here. So it's at that point more complicated. And actually gets even more complicated if you want to go to yet higher accuracy then that evolution equation basically changes, and you would have to include 3 jet functions and 1 to 3 processes and so on. So it's different than DGLAP. It does not basically keep the same form order by order in perturbation theory. And the same thing happens for the factorization. Also, the factorization changes if I go to higher accuracy. So in the leading log approximation, we can think of it in the following way. We have 2 incoming, say, gluons in this case, and 2 quarks in the final state. Then each of those will basically produce a leading jet on each side. And so I basically have to put in my factorization a hard function for the hard scattering, 2 jet functions, and then I basically have to event-wide pick out which one is actually the leading jet if I want to be differential here in the leading jet transverse momentum. And so that basically is here in the last line here in the delta function that basically picks out the leading jet, which comes from either of the 2 quarks. And that, of course, is a lot more complicated, like the structure of that, even at that accuracy than for inclusive jets. And it basically gets more complicated if you want to go to higher accuracy. If you have, for example, 3 partons here in the hard scattering, you have to introduce a 3rd jet function and so on and so forth. So the factorization structure overall is not the same to all orders. So it still doesn't break factorization or anything like that. It's just that you have to put in more effort to do the computation if you go to higher accuracy. So it does get a lot more complicated if we want to think about leading jets, or even subleading jets will get even more complicated. You have to introduce jet functions with 2 variables and so on. So it gets a lot more complicated, but what do we sort of get in return by changing to this as opposed to inclusive jets? And so let me try to summarize that here, what really changed now. So on the inclusive jet side, what we can do basically, or these are basically some rules, if we try to integrate the jet function here, say between 0 and 1, then the jet function is normalized, not to 1, but it's normalized to the average number of jets that are being produced dynamically event by event. Of course, if you actually do the integral, one has to resum small z logs in this case, but eventually you're going to find that it's not 1, but it's like basically the jet multiplicity that you get out. What is conserved though in inclusive jets, since for inclusive jets I basically just take all the jets that I have, is that momentum is conserved. So if I sum over, in this case, these 3 jets, then the momentum fraction of those has to add up to 1, just because of momentum conservation. So the first moment is normalized to 1 in the inclusive jet case. So that basically is what I meant. Like for inclusive jets, we always have to think about number densities. But for leading jets, that really changes. I mean, one can already see it here, like the average multiplicity, jet multiplicity for leading jets, of course, 1, because that's just one of them. And that's indeed the case. So for the jet functions, or eventually the cross-section to be a probability distribution, it has to fulfill 2 criteria. It has to be normalized to 1. And that's indeed the case. One can check this explicitly at next leading order, or one can check it numerically also after renormalization group equation and so on. And it has to be positive. So for all values of z, these things have to be positive. That is true at leading log accuracy. But if you go to, say, fixed order or next leading order, or even with resummation, then that might be violated, but it's only violated if you don't basically, it's basically violated due to the sort of limited perturbative accuracy. But if you include threshold resummation, which becomes relevant when Z1 is close to 1, close to unity, then this is basically justified. And of course, at the cross-section level, if you put in enough resummation, then it will be positive. So it's similar to some QT resummation that it can in principle get negative. But that basically just means we didn't put enough effort into the computation. So that's something that is also satisfied. And so in that sense, we can treat those leading jet functions really as probability densities. And then once we have a probability density, then of course we can compute the average energy loss. So we can compute by weighting it with Z1, we can compute the average momentum fraction contained in the leading jet, and then 1 minus that. So anything not contained in the leading jet, that would be the energy loss. So that means it gets a lot more complicated by thinking about leading jets as opposed to inclusive jets. But we really have this nice advantage that now we can really think about probability distributions. And that's, of course, a very nice thing to So I mentioned threshold resummation, and actually all the figures that I showed you before already had threshold resummation in it. So you basically get these kind of jet functions here that have a peak close to 1. If you don't put in threshold resummation, they're basically divergent here at the endpoint, like integrable divergent, but still divergent. And so if you put in threshold resummation, that basically suppresses the cross section here and goes back down to 0. And of course, these threshold logs appear here in the jet function. So there's different logs in here. The logs in the jet radius, they're resummed by DGLAP. There's small z logs that are not really relevant here for leading jets. And then there are threshold logs that basically matter here in the endpoint on the right. Of course, there's also threshold logs in the hard function. So we basically have to do a threshold resummation both of the hard function and the jet function. And so we have to like set up a joint resummation framework to make sure there's no double counting of both logs in the jet radius and threshold logarithms as well, which is basically a double logarithmic series. And it turns out that's really the relevant one for leading jets. If you want to think about subleading jets, then one has to work a little bit harder. But in the leading jet case, we still get away basically by focusing primarily on the threshold resummation. Okay. Now, the question is still then, how do we actually solve these nonlinear evolution equations? And so there's different ways how one could potentially do that. One is sort of to try to do it analytically, but it's very hard, especially if we want to go down to small z values. Then doing this by hand is very, very difficult. And it's, I would also say it's really not practical or maybe impossible at sort of higher accuracy. And so the only way to really do this is then with a parton shower. And so what we set up in this paper is a parton shower that solves exactly the DGLAP evolution equations. So basically have a shower here in the middle that solves exactly DGLAP evolution. So that we basically make sure that if we ask the shower what's the inclusive distribution afterwards, then we get the exact same result as if we had solved DGLAP evolution analytically. Then in addition to that, we of course have to include in the parton shower itself the hard function and the jet function as well. And so the way we do this is to, by first sampling from the hard function before we start the shower, then we run the shower down to the jet scale, which is basically given by the jet radius. And then for each of the partons that we have, we sample one more time a z value from the jet functions. And then at the end, we then basically perform, so that basically gives us the transition from parton level to jet level. And then at the end, we basically perform the measurement of what's the inclusive spectrum, what's the leading spectrum. So in this sense, this is really not like a multi-purpose parton shower. It does in principle produce you a fully exclusive event. So you could measure the transverse momentum spectrum, things like that. And it probably wouldn't be too far off, but it doesn't have the correct like perturbative accuracy for these other observables. Like one could probably extend it to other things as well. So we're thinking about that, but it's really like a dedicated parton shower to really just solve a renormalization group equation and to do that systematically. So it has really the same perturbative accuracy as it would have if I were able to really do the leading jet computation analytically by hand. So that's really the goal of the shower. It's not meant to sort of do multi-purpose or anything. It's really just solving one particular problem and that's of it. But it's basically a way to put in jet functions into a parton shower, which is really something that you need to have the well-defined or correct perturbative accuracy. All right, so how do we set up the shower? First, we basically just want to make sure it solves DGLAP evolution. So one particular splitting is basically given by these three variables. If you split one parent parton into two daughters, then we need to know the momentum fraction, the longitudinal momentum fraction. We need the relative opening angle theta here between the two. And since we're not going to measure anything about it, about the azimuthal angle, just use flat sampling here for the azimuthal angle. We explicitly do not conserve for momentum because that's also not conserved in DGLAP. So if you want to have an exact solution of DGLAP, we do not conserve for momentum. We just conserve at each splitting the transverse and the longitudinal momentum distribution. So the z value, of course, we get from the Altrelli-Parisi splitting functions. And then to determine the opening angle theta, we basically follow these steps just very briefly. We draw a random number between 0 and 1. We solve this equation for delta t. That's basically the pseudo cofactor. So that's an additional time step in the Monte Carlo time. We add it to the previous Monte Carlo time, so t goes to t plus delta t. Then we take the current value of the Monte Carlo time t, and we solve this equation here for this curly r, and the curly r is related to theta. So that's basically, if you look at the DGLAP evolution equations, then one can basically derive that this is the way we should set up the parton shower to solve the DGLAP evolution equations. Which then, of course, we can check if it actually does that. So there's two cutoffs here. One is basically on a momentum fraction z, so that's an epsilon cutoff here, just to avoid the divergences at the endpoint. In principle, we can choose whatever value we want. The spectrum will only be valid when we're basically within those bounds, if we look at the final result. And then the cutoff is basically determined by this r value here, so we'll be evolving between the hard scale and the jet scale. And so this opening angle theta is basically what determines the cutoff or the end of the shower. And so, of course, as in any shower, we'll iterate this process, and we run, as I mentioned, between the hard scale q and the hard scale of the and the jet scale, which is q times the jet radius, and then we basically produce these fully exclusive event distributions. And so, as a first check, of course, we have to make sure that it agrees with like an analytic solution of the DGLAP equations, and that's indeed what we have. If we look at the leading order or leading log jet function here for gluon, then we can compare here the results from the parton shower and basically an analytic Mellin space computation of the DGLAP evolution equations. Then we find basically full agreement. And so that basically makes sure that if we ask the shower the same question, that we can also answer with an analytic calculation, then we get the exact same result. And so then it basically allows us to extend this also systematically to the leading jet case. So what we still have to put in, as I mentioned, we need the threshold resummed hard functions and jet functions. And so the way we do this effectively, if you think about the inclusive jet case, is that we need to compute basically this integral here of the evolution kernel and then of the jet function, the hard function. And so the way this then works, we also include a non-perturbative shape function very close to the threshold, basically. That's also a nice thing to have because we can basically from first principle say how it should scale with certain parameters. So we have a well-defined non-perturbative component also in the shower. And then basically what we do is we, as I mentioned, we first introduce the hard function, then we run our shower, and at the end, we introduce the threshold with some jet function, and then we perform the measurement here at the very end. Sort of after the parton to jet conversion happens. So we're not running down to sort of like a normal shower cutoff to like 1 GeV, but we're just running down to the jet scale. Then we include the jet functions, and we perform the measurement of the leading jets at the end. So just as an aside, the threshold resummation is normally something that is not included in things like Pythia and multi-purpose parton showers. There you basically get the endpoint right, sort of by other ways. But to really make sure that we have the correct log counting, we really need to include the threshold resummation here in the shower. Okay, so with that, let me move on to some numerical results. So let me start basically with the simplest case, which is E plus E minus to the leading jet. And make it even simpler, we're not asking for the leading jet in the entire event, but we're just asking for the leading jet in one specific hemisphere. And so the event display that we'll be getting shown here. So we have, say, 2 leading jets in an E plus E minus event. And we basically cut it here. There's different ways how one can define hemispheres, and pretty much any of those methods works. And then we basically just look for the leading jet here on one side, as opposed to basically having to deal with the leading jets on both sides. And so that basically makes sure that we have a relatively simple factorization at leading log. So here we don't have like 2 jet functions, but it's just one parton at leading order, and at leading log that will produce one leading jet. And so that basically has the correct structure such that all the 3 criteria that I mentioned at the beginning are basically satisfied. So we have a well-defined object, we have the leading jet, then we know the reference scale here because it's E plus E minus. So we know the initially available energy, we know the center of mass energy, and it has the correct factorization structure so that when I measure the leading jet here in the hemisphere case, if I take the momentum or the first moment of that cross section basically factorizes, and at leading log, it's a direct measurement of the basically parton energy loss to sort of the leading jet. So I would basically take the first moment of the cross section, I think I have it on the next slide, and then basically what I get is what I before always talked about as a jet function level, which means that I weight this here by Z1 and then take the interval over all the allowed values. So in that sense, that basically allows us to directly quantify energy loss. And so this is sort of the simplest way one can do it, and I'll show some results for the energy loss on the next slides. So the entire spectrum, though, is shown here. So this is separated here for quarks and gluons for LEP energies and a particular value of the jet radius. Of course, the gluon case would be a little bit difficult to do in actual experiments, so this is more to illustrate things. And so here you can now see both the inclusive jet spectrum and the leading jet spectrum. In both cases, of course, we have this peak here at large values of Z, and they actually completely agree up to Z equals a half. So whenever I find a jet in that region with that energy, it's of course automatically the leading jet. So in that sense, they agree in this region. But then below 1/2, the leading jet cross section goes down to 0, whereas the inclusive jet cross section goes up. It diverges here, or you would have to think about small z resummation. And the difference between the two is, of course, then the second and third and fourth leading jet and so on that start to matter here in this region below z equals a half. But so yeah, so in this region, it's basically the same. And so from the leading jet spectrum, we can then compute basically the average energy loss. It's a normalized distribution. So this one is not normalized. The inclusive one is not normalized because it's number densities. But here, this is now really normalized because the underlying jet functions that contribute here are normalized to 1. And so from here, we can compute directly the average energy loss. And so the result for that is shown here. So we basically take the entire cross section. So this is not at the jet function level anymore. This is really at the cross section level where we can really do a measurement. So we weight it by Z1, and then we basically just integrate it, and that gives us an average momentum fraction Z1. Then to get the energy loss, we'll just do 1 minus that. So anything that's not contained in this one hemisphere leading jet, that's what we would want to call energy loss. That's basically as close as possible, we would say, to sort of this initial idea of energy loss. We can do a computation of this at next to leading order, of course, from the jet functions. But to do numerics, that's basically not sufficient. And so here's then the result for the energy loss. So that was basically the goal of all this, is to really assign a number. And of course, it changes as a function of the jet radius. This is now shown here again for the plot on the previous slide. And it's shown separate for quarks and gluons. And so basically, if you make the jet radius smaller, then of course the energy loss will get larger because all the additional radiation is not captured, say in that cone of a given site, radius r. And so you of course see the energy loss to go up. So it basically starts here. If you choose a large radius, something like 0.8, then the quark energy loss is around say 10%, gluon maybe like 20. There's relatively large uncertainties here that we assign here. It's sort of more on the conservative side in terms of QCD scale uncertainties, but one could probably, I don't know, there's different ways to assess the uncertainty here. But generally, we find a relatively small energy loss if we choose a large radius. That's of course expected because we have this peak at large values of z of the distribution. And only if I basically lower the radius, then these sort of get slowly smoothed out and move towards smaller z values. And that's sort of what we see here. If we make the radius smaller, then they sort of almost go up in parallel and eventually reach an energy loss of up to, say, for gluons, 80%. So if you choose a very small radius, I mean, that's of course beyond what you normally do in an experiment, but if you choose a very small radius, then the average energy loss averaged over all the events is something like 80%. Of course, if you were to look at even hadrons, if you were to look at the leading hadron in the hemisphere, that would be at even larger values of the energy loss. So on average, of course, leading hadron contains only a very small fraction of the initial, the available energy. Okay, so in a sense, this is basically what we wanted. We have a particular number that we can assign and say, well, in the vacuum, we have an energy loss of 10%. And then if we do a measurement of this in heavy ion collisions, then maybe that will go up from 10 to 20% or something like that. And so we can really assign a very specific number. So one thing we notice is that, as I mentioned, this sort of goes up here somewhat in parallel. So we wanted to look at specifically differences between quarks and gluons. And that's what you can see here. So on the left, in this figure, you can see the ratio of the quark energy loss to the gluon energy loss, again plotted as a function of the jet radius, where smaller jet radius is here on the right. And as you can see, this is actually surprisingly stable. If you look at basically values that are experimentally accessible, something like 0.8 down to maybe 0.1 or a little below. And so you basically find that there's almost no dependence here on the jet radius, and the core gluon energy loss is actually quite stable. The other thing that we're kind of surprised about is that the difference between the quark and gluon energy loss is actually quite small. I mean, this value here is at 0.6. It was actually relatively close to 1. And I wasn't really expecting that, because if you think about basically a leading order soft approximation, so in the soft approximation, we can of course say what energy loss is. And then it's the only difference here is really because of the color factors. So the splitting function simplifies, and you basically just left with the color factors. And if you take a ratio of quark over gluon energy loss, then it should be something like CF over CA. And well, the numerical value of that is 0.44, and that's what we show here in the dashed line. So the vacuum difference between quarks and gluons would be something like 0.44. That's what we sort of expect from sort of this naive leading order approximation. And as it turns out, if we do basically the full calculation with all the resummation and whatnot, then we actually find that the energy loss is large. Oh, sorry, the difference is actually less significant. And that's something I didn't really expect. I somehow thought it should be down here, because somehow this maybe will get exponentiated or something like that. But because they somehow evolved together, the energy loss of quark and gluon jets is actually not that different. So I don't know if that should be surprising or not. It was surprising to me. We checked it several times, because that, of course, eventually matters for heavy ion collisions. If we basically find that the energy loss of quarks and gluons is more similar than we would think in the vacuum, then of course that has implications also of how we think about energy loss and quark-gluon differences in heavy ion collisions. So that's basically what we find, and of course one has to see, does that agree with experiment, and then has to think about what that means for heavy ion collisions. So another thing is that, of course, we not only have to look at the average energy loss. Now that we have a probability distribution, we can look at all kinds of statistical quantities. And so sort of the first thing, besides just looking at the mean of a probability distribution, you can also look at the variance of a probability distribution. That basically tells you about how it's distributed, what are the fluctuations, and so on. So we can do that. So we now basically take here also the second moment from which we can construct here the variance sigma. And you can see the result here on the right, again, with very conservative errors. For lab energies here, again, plot as a function of the jet radius. And you basically see that there are quite significant differences between quarks and gluons. They basically cross over here. And that basically means that sort of the distribution as a function of R changes in a very different, somewhat in a different way, sort of where it's peaked and sort of becomes broader or narrower in a different way for quarks and gluons. So that's in principle also something that one could measure, and it sort of gives basically the variance of the energy loss distribution. So that would also be basically a new thing one can look at and try to quantify the underlying probability distribution. We also wanted to compare basically how different quarks and gluons are. And so what we're looking at here as an example is the KL divergence. That's something that's often used in statistics. We also looked at, for example, ROC curves, which is maybe more standard for quark-gluon tagging, but we decided to use this one. So the way the KL divergence is defined is this integral here, where you take the logarithm of the ratio of the quark and gluon jet functions. Or well, eventually the cross section instead of the jet functions, and then you weight it by one of them. And so, of course, if they're exactly the same, then this ratio is 1, so the log is 0, and that basically means the more different things are, the larger your KL divergence is. And so the result for that is shown here on the right, again, for 2 different values of the energy scale Q. And sort of the interesting thing is that if you look at this, it basically peaks in a perturbative region. So for a perturbative value of R, say 0.1 or 0.05, that's basically the region where quark and gluon jets look the most different. If you go to larger or smaller radii, they will look more similar. And that's, of course, pretty good for quark gluon tagging, because it means there is sort of an optimal value where we can look at leading subjets, and that should give us a very good discriminant between the two. And that's kind of nice that it does that in the perturbative region, because it means we have this tagger basically, or this classifier on a very good control, versus other things such as multiplicities and so on. They basically get, they are very good in some ways, but they sort of are very good because they're sensitive to non-perturbative physics. And so then we don't really have it so well under control and can be a bit more problematic. So in this sense, this would be basically something where we can then compute ROC curves and quark gluon tagging and so on perturbatively, and we can actually optimize it with a particular value of the jet radius. So it can be relevant, sort of maybe in a boosted decision tree, sort of with other observables as well. Okay, now before moving on to PP collisions, let me still show you the result for event-wide leading jets. And so here, unfortunately, I don't have the factorization formula here, but as opposed to looking at hemisphere leading jets where we have it leading or just 1 quark, now we'll basically have 2. And so here we have this more complicated factorization that I showed you before, where we have a hard function and 2 jet functions at leading log, and we have to then basically event-wide pick out the leading jet. So this is more complicated to do. It can all be done in the parton shower directly, and then we can basically perform the measurement of the leading jet in the end, event-wide. And so here, the interesting thing, what you can see here, so this is the result here for the leading jet distribution. We also compare here to Pythia, which is just pretty good, and it's of course very well tuned to E plus E minus collisions. So that's good. And then we compare here to the inclusive jet distribution as well in this dotted line. And that, I mean, as you can see now, this does not only disagree with the inclusive below 0.5, but it already starts to disagree here at very large values of Z. And that basically just is, I mean, this is of course expected, because now we basically have, for the inclusive case, we would always take at least 2 jets per event and put them in histograms, versus the leading jet cross-section event will always be just a single jet per event. And so in that sense, they already start to differ, at very large values of Z, versus for the hemisphere case, it only starts to differ at small, right, like at 0.5. And this is actually something that can be measured. So we expect there will be new data coming out, but there's already some data from the Opal collaboration that we found. Unfortunately, they had a little bit of a different setup, which doesn't allow us to really compare quantitatively at this point. It had like some somewhat strange algorithm at the time. But you can see what they measure basically is the leading, second and third leading jet. And you can see basically this has this kind of structure here for the leading jet, and it sort of qualitatively agrees. Quantitatively, it doesn't quite agree because they did a different procedure, but we expect basically new results to come out in this direction as well, because people are reanalyzing that data. So one can directly compare, and then, for example, one can check here, are these non-perturbative effects that we include, are they actually well described? Do they scale correctly with the jet radius and things like that? Now, okay, so the question is, how can we now measure energy loss and to basically assign a number in PP or in heavy ion collisions? And so the first thing we thought of was to basically use photon jet correlation. So we measure a photon, and then we look in the opposite hemisphere and we measure only the leading jet. And then we construct this quantity xj gamma or j1 gamma, which is the leading jet transverse momentum relative to the photon. In this case, we do have basically a factorization structure that would allow us to access the energy loss and to really quantify it by basically taking here the first moment of that resulting cross-section differential in x. And basically what we find is then basically a weighted average of the momentum fractions, the leading jet or the energy loss momentum fractions of quarks and gluons. So that in principle works. The only thing is this variable here, of course, is something that is not bounded between 0 and 1. And so that basically, I mean, it is, of course, a leading log, but in general, it's not. And so we have here a result, for example, looking at this in Pythia, where you basically see this variable is not bounded between 0 and 1, but it actually goes, it's basically unbounded, it just goes up. Even though it sort of drops rapidly in this region above 1, but it's like higher order corrections that basically are important in this case. And so it's not a variable that's basically between 0 and 1. One could in principle still measure energy loss like that, basically by comparing the inclusive and leading distribution over here. So one could basically put in a cut and basically come relatively close to something that we could also do in E plus E minus collision. So it's definitely a way one could do it in principle, but there's also an easier way to do it, which is to basically use jet substructure as a tool. And so what we do here is to first reconstruct an inclusive jet with a large radius r. So that would basically generate us a reference scale with respect to which we're going to measure the energy loss. So this Q would be basically the reference scale Q here would be set by the transverse momentum of that leading jet. And then what we do is basically just take all the particles that you have in the jet and recluster them with a smaller radius r. So it just has to be smaller than the initial r. And then we may basically just measure the leading subjet in that initial jet. And we just measure what's the momentum fraction that's contained in the leading subjet relative to the initial jet. And so in this sense, we've basically constructed ourselves a reference scale with respect to which we can measure this. And then since everything is, of course, universal, the jet functions have to be universal quantities, we're basically measuring the exact same thing as we would say in E plus E minus, or if we had a photon there. And so at leading log, we have a factorization structure where we can basically absorb everything else of the cross section in some hard function that doesn't depend on Z1. And then everything else is basically, again, the usual jet function. And so in that sense, again, all three criteria are basically satisfied, and we can extract the energy loss. In this case, again, it would be, of course, and somehow an average quantity between quarks and gluons, which one can, of course, also try to disentangle in certain ways. And well, here are the cross sections for this. For given LHC kinematics, the leading jet, and the inclusive jet cross section. And that, to some extent, I think would sort of be the easiest way to start doing these kind of studies and to basically assign a value of energy loss in proton-proton or heavy ion collisions. And so before coming to the end, let me also, I guess running a little bit out of time, but let me just show these very recent results from Alice, where they actually did exactly that measurement. And they were a little bit fast, so we're not able to provide the predictions that they needed to do a one-to-one comparison here in PP collisions, because they measure charged jets, we can only compute full jets. So that's sort of always a procedure to do the comparison. But more or less things look sort of as you'd expect. So here what you can see is on the left is the leading subjet distribution as a function of this value ZR. So there are basically two values of the jet radius. The initial one is 0.4. And then for the subjets, they were reconstructed here with 0.1 and 0.2. And here on the right, you can see the inclusive subjet distribution. So they're usually only able to measure this well up to a certain value of 0.6, which may improve in the future to sort of map this region out here a little bit better. But the inclusive, they can basically measure over the entire Z range. And so we can basically directly compare, has this expected peak structure here at basically the endpoint of Z close to 1. And this also has a peak basically here in the smaller Z region. And so in this sense, we can basically check if our calculation actually works the way we would hope. And actually what they also measured here, and these are basically these values, let's say 60% that I mentioned initially with a laser beam. Here is basically now the energy loss that they measure in experiment. It's either 10% or it's 20%, depending on which value of R you choose. And so in this sense, these are, I would say, sort of the first results to really quantify energy loss sort of at the cross-section level here in the vacuum. And there are even results in heavy ion collisions and how they get modified, these leading subjets, I mean, so they measure this, well, in the region between 0.6 and 1. In that region, of course, the inclusive and the leading subjet distribution are the same. It would only differ below 0.5. So hopefully this can be extended in the future. But the interesting thing is that you can actually see that it changes in heavy ion collisions. And that's, of course, what we're hoping for. So you can see in blue the result in PP collisions, and then in heavy ion collisions, 0 to 10% centrality with a particular value of R. So it basically corresponds to this diagram over here. You see that this really changes, and that basically then, I would say that's really the difference in energy loss due to medium effects. And sort of as a little bit of an aside, we actually made a sort of a predictions for this using, that's basically shown here in green, using something that we did a while back with Jianwei Chu and Nabu and Pierre Surita. In that paper, we basically made an assumption, or we tested it basically, we tried to test it, whether this inclusive jet factorization that I showed you in terms of heart function, jet functions, also applicable in some way to heavy ion collisions. And so we basically just try to extract these medium jet functions from the inclusive jet data. So that's what you can see here. These are the medium jet functions for different energies for quarks and gluons relative to the vacuum. And so, of course, at that point, I mean, this kind of worked. And we were able to extract these things, but of course, just extracting them, I don't know, that doesn't really tell us a whole. I mean, it tells us that the factorization is not completely crazy, and we get out something that's reasonable. But eventually, you have to really check if there's some universality, and whether you can use those jet functions also for other observables. And so, the only observable really that relies only on the jet functions is if you look at basically subjets, because in this case, your factorization more or less looks like this. It's a little bit simplified, but it has sort of the main structure. We have two PDFs, heart functions and a jet function. And then to basically produce the initial jet of size R, and then you have another jet function that tells you how the subjet is produced. That is now a function of ZR. And so if there's universality in also heavy ion collisions, I mean, there's definitely universality of these jet functions in PP collisions. That's something you can prove, but the question is there also universality of these jet functions in heavy ion collisions? And so that basically gives an opportunity to test if this actually works. And so if there's universality, all we really have to do is we have to switch out these two vacuum jet functions for medium jet functions that are extracted from the data. Of course, this is now a much more differential measurement. Here, this was basically in the inclusive jet cross-section. Right here, in the inclusive jet cross-section, you never see like this peak at large Z because it's convolved with like very steeply falling heart function. So there's never a peak there, right? So we're basically extracting this from something where we don't have basically a Z variable. So it's much more difficult to actually get the information. So it's really not necessarily clear that this should work, right? That you get enough constraints from inclusive jet data to actually look at this more differential quantity. But it seems that actually works surprisingly well, which I think is rather encouraging because it tells you that there's some potentially really some universality in all this. So what we did is we just to switch out the vacuum jet functions here. That gives you basically an overall quark gluon fractions. So basically medium quark gluon fractions. And then we put in here the medium jet functions as a function of ZR, and we get this green curve, which to be honest looks like surprisingly good, I would say. And so this is sort of, I would say, sort of a first test that some of these tools that are developed in terms of jet functions and perturbative calculations in a vacuum really also carry really over to heavy ion collisions, because in principle, that's not necessarily clear, right? You could have some contributions in heavy ion collisions that just mess up these factorization theorems. But it looks like, at least there's some first indication that that's not, that's not necessarily the case. One thing I still wanted to point out before coming sort of to the end, what we found here, and that's sort of a little bit of a question to me, and it's not really clear what the answer is, we found a very large difference between quark and gluon jet functions. Sorry. So basically, between their modification, you see that the gluon jet functions here are very much modified, whereas the quarks are not very much modified. And that seemed to be fine at the time because, I mean, a priori, I don't really know how much they're modified sort of relative to each other. But now we basically found that in the vacuum, the energy loss of the leading jets of quarks and gluons is a lot more similar than you would expect. I mean, the ratio of quark and gluon energy loss was relatively close to 1. And so, I mean, it's not really directly a contradiction because one is like leading jets, the other one is medium inclusive and so on. So it's not really 1-to-1, but still, I'm not quite sure if, sort of what the conclusion is about this. So on the one hand side, we find quark-gluon jet energy loss quite similar. In the vacuum, in the medium seems very different. I don't know if that's true, but at least so far, it seems to give relatively reasonable results. So it's, of course, something one has to investigate a little bit more in the future. So with that, let me come to my conclusion. So I talked in detail about the difference between inclusive jets, and we basically argue that you cannot assign a value to the energy loss at the cross-section level with inclusive jets, but you can do so if you sort of go through all this pain of calculating these more complicated leading jets. But then you get a probability distribution. You can write down what you mean by energy loss, and you can compute it basically as a single number. Of course, as I mentioned, it gets more complicated. The factorization evolution changes order by order perturbation theory. But with that, we can basically quantify energy loss. As shown here, one can extend this, for example, to leading and subleading hadrons. That would basically give you a non-perturbative notion of energy loss. And then, of course, from here on, one can, of course, do computations of this and think about how this gets modified in heavy ion collisions. So with that, thank you very much.
Thank you very much. We start with the question. Let me stop the